Welcome to the Math Record. Today I'll be covering the final video for our whatever class for the end of March. So the topic today is finding out the relationship between common internal and external tangents. So what is a common internal or external tangent? Well, a common internal or external tangent, let's first make a line. Now let's draw two circles. Because tangents are going to be with circles, and we have let's say a smaller one right here. And let's say we have a bigger one right here. So we're going to do a general case. Okay, and they're not going to be touching each other. They could, but for general cases, let's just say they have a distance apart. Okay, so our common external is going to be the length of the line that is common to both these circles, is tangent to both these circles, right? So common external tangent. So it's external because it's from one end to the other. So it's going to be the same thing as like right here, right? So what's a common internal tangent then? Well, a common internal tangent is gotta go from like a top of the circle to the bottom. So it's gonna be something like this, right? Let's draw a little bit more precise, like this, right? Where we have a point up here and a point down here, and that's our common internal. And they're gonna be different lengths. And I could prove why when we derive our formula. So let's first do our external. So how do we do this? Well, let's first label our variables to see how everything works. So we have a center, actually a little bit higher, I think. And this length right here, we're gonna call it the smaller radius, so it's small r. And the bigger radius is called big R. And now let's connect those two centers together. Okay. And now let's draw a line that is perpendicular with this line. I mean parallel with that line. So we're gonna go from here all the way right here. And delete. So the reason is now we could redefine this. So we know this one is parallel to this line, and this is a right triangle because it's tangent. So this is the same case because it's tangent. And since this line is parallel with this line, because that's what we set it as, then this is going to be a right triangle, and this is going to be a right triangle because this is a right triangle, right? So no, all they're right triangles. I mean, they're all right angles, sorry. So if this is the smaller radius, and since this is all parallel to each other, it's just going to be a rectangle. So this is also small r. And remember, this entire thing is big R, so this is big R minus small r, plus small r is big R, right? So we could also define this as small r, big R, and let's call this one distance d, and we're going to call this our external. So since it's a rectangle, this is also external. So now we're just going to use this triangle, right? This triangle right here. So use the Pythagorean theorem. That means e squared plus a r squared, r minus smaller r squared equals big R plus small r plus distance squared. You can write it however you like. I just like to put it in order because, it looks nicer. So now we have e squared plus big R squared plus small r squared minus 2 big R squared, small r squared, distance squared plus 2 big R small r plus 2 big R d plus 2 small r d. So let's cancel out similar terms. So bigger case r, smaller case r, and this one would go over here. So that means our e squared is going to simplify out to d squared plus a 4 now, because we added the 2r from 2 big R small r from this side, plus 2rd plus 2 small rd. Okay, and I'm going to rewrite this such that it kind of looks a little bit easier to simplify. So we're going to put a d squared here and 2rd, then plus 2 big R d plus 4r big small r. So I just moved it around. I just moved this one on this side. This one stays same, and then this one moves over to here. Right? I just switched those two positions. So the reason I did that is now we could see it a little bit easier. It didn't really change into the math. So then we did the d, just withdraw the d out, right? Distribute the d out plus 2, right? So d times d is d squared. D plus 2r is 2rd. And then we'll do the same thing here. So we distribute out a 2 and a r, and 2 and a big R, I mean. So it's going to be a d plus a 2 smaller case r. Oh, we see like terms here, right? So now we can simplify this as 2 smaller r plus d plus 2 bigger R plus D, right? Because you put these together and these are the same because it distributes out, right? Perfect. And I just put the radius in front because I like to. So that means our E is going to be equal to the square root of 2 small r plus D plus 2 big R plus D. And that is our formula for our external. Okay, so now we can delete all this because we don't need it anymore. And we have this equation. So now we need to find our internal. So let's draw the line again. So somewhere like right here. Okay, looks fine. It doesn't have to be overly precise, just draw like a general equation. So our tangent point is right here, and our tangent point is right here. So now we're going to connect the two centers again, like what we did before. Okay, looks fine. Okay, so how are we going to find the length of this internal now? Well, let's actually kind of move this line a little bit up, right? So we're going to go up. So that means our line is going to look something like this. I'm not the best drawer. Looks fine. Okay. And then we're going to connect this point, this center, all the way to that line. Okay. So let's kind of prove a few things. So this is our smaller radius, this smaller radius, right? And bigger radius and bigger radius. So, and now, next, let's put this one right here. And then we're going to draw this line right here. So this is our bigger radius. So we know that since this line is tangent, this is our right angle, and this is a right angle. And since we just moved this line over here, that means it's parallel and also the same. So that means this is also going to be a right angle, and this right angle. So this is now our rectangle. When we were working was like right here. Now it's going to be up here. So that tells us that this length on this side is also big radius. And um, actually, we don't need to have this radius anymore. Okay, sorry about that. That was extraneous information. So this is our internal tangent. So that means since it's a rectangle, that means we'll move it up here, which is what we moved up to, and that's I. And now we can just focus on this triangle. Now, let's put our D in here, our distance from here to here. So that tells us that the internal tangent squared is equal to our, internal tangent squared plus the other leg, which is big R plus small r squared is equal to big R plus small r plus d squared, right, using Pythagorean theorem. So this looks awfully similar to our external, right? When we were working with our external, we actually minused here. In our internal, right, we actually now we're adding. So there might be a relationship, which we're going to find out in the end. So our internal tangent squared, plus radius squared, upper bigger radius squared, smaller radius squared, plus 2 big R, small r, upper radius, smaller radius, uh, distance, and 2rd, 2rr plus 2rd plus 2 small rd. Cancel out similar terms, and this one cancel out with this one. So that means I squared is equal to d squared plus 2RD plus 2RD. Okay, so now we can't simplify like this now, right? I thought they were similar, right? Because it's right here that looks pretty similar. That was just different. So how do we get that kind of equation again? Well, let's kind of work with this. Let's just manipulate some variables around. So let's distribute our d first, and then that's d plus 2r. So now we need a d plus 2r. So let's put it right here, d plus 2r. So remember, we can't make up new terms. So we need to somehow simplify to the rest. So d times d is d squared. D times 2r is 2rd, right? And now we need this term. So how do we get this one? We have a d here already, right? So we need the 2r. Okay, that means so plus 2r times our d is 2rd. And now we have a extra 2r times 2 bigger case r. So we have to take that one out. So 2 times 2 is 4, and the 2r's, uppercase r, lowercase r. Okay, so that means I squared is equal to, now go put them together, which is 2r plus d and 2 lowercase r plus d minus 4 bigger case r minus lowercase r. That means I, which is our common internal tangent, right, is equal to 2r plus d, 2 lowercase r plus d minus 4 uppercase r lowercase r. And that is our equation for our internal tangent. Okay. And a little bit more part here. And now let's find the relationship between these two. Let's move this one down. This one up a bit. Okay. So using this idea, okay, let's kind of clear this picture. Need all this work anymore. So using these formulas, what's the relationship between external and internal, right? Because they both have similar parts. So what we could do is we could square both of them. So e squared and I squared, right? External squared, internal squared. That means it's just going to have, without the square root, just these terms inside. So we could just move this thing over here. So that is equal to e squared minus 4r squared. So that gives us that in our relationship, oh, sorry, and is 4r squared is equal to e squared minus I squared. Okay, and that is the relationship between our internal and external. So the difference between the squares of the tangents is going to be equal to 4 times the product of the radius. So the external tangent squared minus the internal tangent squared is equal to 4 times the bigger radius times the smaller radius. So what does this basically tell us? Well, that basically tells us that external is always going to be bigger than our internal. So why is that though? Well, the reason is because if you look at these formulas, right, we have both the same term here. So let's say this was some kind of number, right? This number is just going to stay this number and then square root it. But this number over here, we have to subtract something. So when we always subtract something, it gets smaller. So then square root of a smaller number means a smaller number. So that gives us that our internal is going to be smaller than our external. So usually the only way for this to ever be of like any maybe bigger would be if there was fractions, but that's really unlikely. So when we're using integer values, usually external is actually always going to be bigger than internal. So external is always bigger than internal, which makes sense, right? Because if we draw a line from here down to, oops, sorry, from here down to here, this length is definitely shorter than from here to here, right? Because this one like starts, let's go down here and go right here. is like this length right here, while our external is like this long. So generally, if you want to memorize the formula, you just need to know that we have to be working with squares. So which one's bigger? The external, right? So external squared minus internal squared is equal to 4, some kind of magical number, times the product of our radius. And that's basically it. I hope this was an interesting video to conclude for the end of March. And if you want to learn anything else, maybe check out the rest of our whatever classes.